conversational AI engineer at Swisscom. She's a data scientist and computational linguist, and her current role involves building conversational AI systems, that is, chat and voice bots people actually want to talk to, for Switzerland's largest telecommunications provider, Swisscom. Her talk is titled, Where There's a Will, There's a Way, the mad genius of LLMs as classifiers. Please welcome Katherine.
Thank you. Test 1, 2 for the sound guys. All right, yeah, so thanks so much for having me today, everybody. And my name's Katherine. Yes, I'm a data scientist with a background in computational linguistics. Please do connect. You can find me online. We will be giving away one copy of this book this afternoon, so do stay till the end so I don't have to carry this heavy thing back home. Yeah, let's get started. So today I want to talk about LLMs as classifiers, why that's a bit of a weird idea, but you might want to try it anyway. And we'll ground that in the real-world use case that we're doing at Swisscom, which is intent detection. And I'll go at lightning speed through some possible architectures and techniques. I've got tons of QR codes and stuff on the slides that I don't have time to cover, so just take photos so you can check those out later. And then to make it more useful for all of you, I'll try to generalize that then to other classification tasks. So firstly, why do I say LLMs as classifiers is a bit of a weird idea? Let's think about what classification is. Thank you so much for the great introduction in the last talk. Classification is where you have a machine learning model and it's classifying some input with some specific label of a specific class. So things like cat and dog detection, spam or not spam, all this kind of thing. Now, on the other hand, large language models, they're complex algorithms. They can solve very diverse, different kinds of tasks, and they usually have long-form outputs, not just one label, but they never shut up, basically. Now, let's go back to classification. It usually needs to be accurate. It needs to be consistent, so the same input gets the same output. Often needs to be interpretable, because if you're, say, classifying if someone should get a job or a loan, you want to be able to understand why a model made that prediction. And it usually needs to be fast, because it's rarely the end goal of the system, it's just one part of it. Now again, let's look at LLMs. They're slow, they're very random, and they're not at all interpretable. And don't be fooled by thinking you can ask an LLM, why did you say this? And it'll give you an answer, because that's as non-interpretable as the answer you're trying to search. So there's clearly some big differences. And LLM is basically overkill because classification models can be quite small and simple. But LLMs can still give us some benefits. They're very useful for prototyping. We see that at Swisscom. It's if you have an idea for how something could work, a system or a product that has a classification component, very easy to just try it out with an LLM. You don't need any training. You can just describe the problem and try it out. And that means that also if you want to add new possible classes or new labels, it's very scalable and flexible. You just add a new description in your prompt. Plus, on a sort of problem description level, if you can turn your LLM problem into a classification task, then you might even be able to, say, use some existing benchmark data sets just to get started, or take advantage of existing data science best practices and evaluation metrics. Another benefit is that LLMs are pretty good with messy data. A machine learning model might struggle with, say, missing features or something, but LLMs can really gobble it all up, even multimodal. And they're multilingual, so that can be quite useful for building in one language and then porting to other languages. So how are we doing this at Swisscom with our chat and our voice bots? When our customers call us, we have to quickly and accurately route them to either a customer service team or maybe one of our existing self-service use cases. These cases work really well. We just need to get the customer to the right spot. And that means we need to detect what's the product and what's the need of the customer. So clearly, that's a classification task. Now, it's tricky because customers can express themselves in many different ways, which can be confusing even for humans to review a transcript and figure out what they want. Meaning is often also built up across multiple turns of dialogue. If a customer calls and says, I have a problem with my mobile, we might ask, okay, is it technical or administrative? And they say, the first one. And then you can only understand that with the whole conversation. And so that changes the problem a little bit. Context also plays a factor. If they call and something's not working, we see they have a service that's blocked in their whole area, that will help us detect their intent. Another big problem is that customers don't always know what they want or they need. So they might call and say, I need to cancel my abo, and so that would be a cancellation intent. But a good agent might figure out, no, they're just having some financial difficulties. Really, they don't want to lose the service, but they need maybe a cheaper package. So that could be a sales intent. So the customer doesn't actually know what they need. And similarly, customers, how they think about problems and how our business is structured to help them can be different. Because if they call and say, my mobile's not working, sounds technical, right? Maybe they didn't pay their bills. They need to go to the billing team. So again, that can be tricky, and customers can have multiple intents. And of course, as we are all data scientists, we know there's always noise and garbage in the data as well. And here's one of my very earliest blog posts about why natural language processing is hard, sad face. But we do it anyway, because intent-based logic can give us some benefits. Firstly, it helps us just as development teams. We're cross-functional teams. We need to simplify natural language to make it workable. We can think about different customer experiences by understanding typical journeys that customers might take. Having a classification step can make our system a bit more deterministic and interpretable, and therefore also testable, because we can see at this stage it predicted this intent and what happened next, and it means we can create benchmark data sets and try to also test that. So that's useful. Also, having intent detection or classification in general can help reduce, say, hallucinations and improve efficiency, because if we just had an agentic system where we said, you just figure it out, then it might make a bunch of unnecessary calls to different tool APIs to try to overcomplicate things and hallucinate stuff. And if we're saying, no, just predict the label, please, that can simplify that. And let's not forget, Swisscom's a big business. We have other teams that need to do reporting. They need to organize how many staff they need in different kinds of the support teams. So intent-based logic can help with that as well. So again, back to this agent topic. Some of you might be thinking, well, if intents are so hard and LLMs are so great, why don't we go full-on agentic, where we really let the bot figure everything out on its own? We could. But a lot of cases, that's, again, overkill. As I said, we already have the solution. It's been there for years. We just need to get the customer to the right place. We don't need the LLM to get all creative and spontaneous on us. So we treat the LLM like a front door that is just guiding the customer to the right place. Another reason not to use agents is that your customer contacts are your most valuable interactions. Maybe you don't want to trust a rogue LLM with that. And it's also just good prompting practices, because breaking a problem down into smaller steps, we anyway know that that does help when working with LLMs. And I'm not saying that we shouldn't use the LLMs at all, therefore. You can use it for other parts of the system, like to handle chit-chat. They're really great, much better than old systems. And of course, RAG, Retrieval Augmented Generation, where you're basically, as a fallback, you can generate answers to very random questions from some documents. So now let's look at possible architectures. So again, I'm going to keep super high level, just photograph the slides and check them out later. To give you the baseline, what I would call the classic architecture, what most systems used until ChatGPT, was a natural language understanding bot, where you have a machine learning model that does maybe the intent and topic detection. Then on top, you have some business logic encoded as rules, even syntax matching, to try to figure out then where should this customer go. If you want to put an LLM into this system, there's still benefits there, because instead of hard-coded utterances, you can now start to have more natural-sounding ones. The pros are that machine learning models can be simple, fast, interpretable, trained for that specific problem, can be easier to evaluate them more concretely. But as I mentioned already, adding new classes is hard because you need whole new labeled data and you need to retrain. But many systems do look like this today. So let's see, how can we start to put an LLM into this system? The hybrid is what I'm calling this. You could use a machine learning model for the initial classification, but whenever the prediction uncertainty is high, so the output label has not a very high probability, you could just only then go to the LLM. So that would give you all those benefits of the machine learning model, but the strengths of the LLM, but only when you really need it, so it's a bit cheap. Of course, the cons, though, is that anytime you add an LLM to a system, it becomes more complex to deploy and maintain. Now you've got machine learning models and LLMs. They're expensive, slow, opaque, unpredictable. But nevertheless, some companies are trying it, as you can see in this cool podcast. Another kind of similar approach, I'll call it the filter. Instead of getting just the top 1 intent from the machine learning model, you could get the top 5 or 10 or whatever, and then just inject those into an LLM prompt. So instead of saying, hey, these are all our 50 possible intents, please route the customer, you could say, hey, LLM, which of these 5 is it? And that will help you recover from maybe poor accuracy of your machine learning model component, but the cons are the same as before, the complexity and costs and things. But VoiceFlow is another real-world framework that does do this. Now we come to what we're doing in my team. I call it the fast learner, but it's just few-shot prompting, which you probably also know. So again, you just have a big prompt where you're saying, your job is to route customers to one of these different categories, and then you have the description of each of the different intents. Now, this takes advantage of the out-of-the-box understanding and capabilities of LLMs, which is great. Makes it much easier to add new use cases. You just add a new intent and a new description. But we have all the same costs as LLM. Nevertheless, this is a popular approach, and Rasa is one example framework that can do that. And now we're going to stick with Rasa and talk about a variation of this one. It's called the embedder. And this is where the problem with the few-shot inference approach I just described is that the more use cases you add, or the more intents you add, the bigger the prompt becomes. So of course that makes it slower, but also you can get accuracy issues. We see this all the time in practice. You add one new intent and the bot starts to go always to that intent. It starts to steal from the others. So you can get this problem, or just generally lower confidence from the bot, which might cause it to ask unnecessary disambiguation or clarification questions because it's not confident. And so we want to counter that. So what you can do, this is a bit similar to the RAG approach, which some of you will know about. Basically, you get all your intent descriptions, you embed them as numeric vectors in vector space. So, we know vector space, we've got all these vectors pointing in different directions, reflecting the semantic similarity. And then at inference time, you get the customer utterance, you retrieve the most, 5 or 10 most similar intent descriptions, and then put those into the prompt. So it's a bit like the filter that I mentioned before, just a different way to do it. And that can help with some of those latency and accuracy problems. Also add some interpretability because okay, at this point it was choosing between these 5 intents instead of these 50 intents. The biggest challenge, though, is that the way that your bot builders, your conversation designers describe and think about problems is not at all like how customers think about them. So you can find that the intents you retrieve are so semantically dissimilar to what the customer actually wants that you're doomed to fail. So that's a challenge. But again, this is something that Rasa offers. I actually do have time to cover this one. I was going to skip it. This is a bit more technical. This is one I saw on a nice Kaggle podcast. So the thing with next token prediction that LLMs do, that's also essentially a classification task. But it's just that at every next word in the sentence, you're asking it to classify which of this 10,000 word vocabulary is the next token. And so what you could do is, I saw some Kagglers do it, you could attach a custom head to your model, like a gradient boosted tree, and fine tune it to map all the probability distribution of this whole vocabulary to the intent labels, because maybe certain groups of words point quite clearly to one intent versus another. So that's a bit of a fancy one. I was going to skip that because it's a bit more technical, but here's two really cool resources if that sounds interesting for you. Now, what have we tried so far at Swisscom? So obviously we started with the classic natural language understanding bot, had some logical rules and things like this. It was quite advanced actually, but we'd hit a bit of a plateau with how much we could scale and add new use cases. It was just too difficult. So now we're working with a framework that sort of follows this fast learner few-shot inference approach. It's very, very useful. We want to start exploring things like the embedder approach too, because as we're adding more intents, we are having that explosion. And our system still converts audio files to text first, which, as I said, can have some data noise. So we'd like to try multimodal models and see how well they go as well. But what could you guys do? So if you have a classification problem, or if you can get creative and think about how you could turn your problem into a classification problem, then here's some tips. So do just try it out, get some production data, and spend the time to label it. You don't even need necessarily a huge data set, and it can be really worth the effort because it also forces you to think about the problem, especially if it's, like in our case, we have to then understand how the agents think about the problem, which is very useful for when we're then writing our intent descriptions and so on. So do that. Then, like good little data scientists that we all are, establish your baselines. So the size of the largest class, you want to get at least as good as that. And have a look at how your existing classifiers are performing if you have those. And then try out this few-shot inference approach. You can even just try it in like the ChatGPT UI if you want to, or you can wrap it in a very simple for loop that just calls it via an API. It's pretty easy to do. And in terms of which samples you should try, well, you could try two things. If you imagine having that hybrid approach, the very first architecture I mentioned where you only go to the LLM for the cases where the machine learning model is unsure, you could do something similar because you could look at your samples where you've labeled, my old classifier was wrong, and just give those to the LLM, see if it's better, because then you could add the accuracies of the two and get a feeling, is that going to work? Or you could just do the full-on fast learner approach where you're just really trying every single sample in your test set, with this few-shot prompting approach. And then, of course, if the results are promising, then you can look at more complex approaches like adding the filtering and things like this, or even go all in on this fine-tuning option. But my tips, prompting best practices can be unexpected and very model dependent. We see now, because we have to prepare for the fact that GPT-4o is getting retired in June, so we have to change our model. Performance tanked, right? So it's very important to experiment a lot, document what works best for your problem, maybe try to have systems where you will, if you're going to have a system that's going to change model live, maybe because you're hitting rate limits on one model, so you need to switch, bear in mind that the prompts might need to be very different, so you might need to really have the option to switch not just the model but the prompt as well in production live. Please don't forget to include domain experts as well, so like your conversation designers, the call center agents, not just when you're designing the intent description, or let's make it more general, the class descriptions, but also when you're exploring the model outputs, because they might have better feelings of why the model made a mistake. And if you are going to test a public LLM, like in GPT UI, don't forget your data protection laws, obviously. Next, make sure you situate your problem in a business context. For example, what is the cost of different kinds of misclassification? If we miss a complaint, that's maybe more damaging than just missing a general inquiry. And ask yourself if the data is telling the full story. For example, in our case, we were tempted to look at the customer satisfaction scores and the answer of, did this resolve your question, yes or no, as a bit of a proxy for ground truth. Was this a good label? But we know there's a massive negative bias because customers only answer that question if they're really angry. So bear that in mind. And I'm going to leave you on one more cliffhanger. Get clever about how to measure progress. For that, I have another blog post for you. But that's all I have time for. So thanks very much.
Thank you very much, Katherine, for such a wonderful talk. Very thought-provoking, and you covered a lot of information. I will open up for one question. If there's one from the audience, very quickly. I don't see one. So I'll ask the question posed on Whova. What kind of tangible performance issues did you face when you changed the model from GPT-4? Could you list a few?
Yeah, so one of the biggest ones is, as I said, one intent sort of stealing from others. So too many things now going into one specific intent versus another. So that's one problem, so there's stealing. We do see a lot of hallucinations, but luckily our framework kind of ignores those because it can only give a label and then we trigger things more deterministically, but we can see it like just making up random stuff, filling random slots that don't exist. And that's worse with GPT-4o than GPT-4, for example. And then the other thing is lower confidence, where it's less willing to make a prediction, so it instead triggers a clarification question. So yeah.
Thank you very much. Please join me in thanking Katherine for her excellent talk.